Hi, my name is John Krochmalny, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll be investigating electrical resistance. The learning outcomes associated with this presentation are going to be three. Number one, describe electrical resistance. Number two, describe resistance's effect on voltage and amperage. And three, describe how resistance is measured. The term resistance means to oppose, to restrict, to slow down any flow rate. We can also predict any flow rate to the resistance it encounters. The higher the resistance, the lower the flow rate. The lower the resistance, the higher the flow rate. To illustrate this principle, this graphic features a 5-foot pipe having a water pressure of 30 psi. The way this water circuit is configured, we may see a flow rate of 3 GPM, or gallons per minute. If we lengthen the pipe from 5 foot to 15 foot in length, we see a decrease in the flow rate from 3 GPM to 2 GPM. This decrease is due to the pipe's internal resistance to the flow of the fluid. Notice that an increase in resistance results in a decrease in flow rate. Notice also that the pressure on the fluid remains the same, about 30 psi. If we lengthen the pipe from 15 foot to 25 foot, we see a decrease in flow rate from 2 GPM to 1 GPM. Again, this decrease is due to the pipe's internal resistance to the flow of the fluid. Every length added to the pipe increases the total resistance to the flow of the fluid. Notice also that the pressure on the fluid remains at the same value of 30 psi. We can now draw some conclusions about flow rates, the resistance to that flow, and the pressure differences needed to initiate the flow. If resistance increases, the flow rate will decrease. If resistance decreases, the flow rate will increase. Again, notice that the pressures on the system will not be affected by the resistance. If we increase resistance to an ultimate value, for example, a plug being placed into the pipe, this ultimate resistance stops the flow of the fluid. When understanding the cause and effect between resistance and flow, we can look at it from the resistance's effect on that flow. An increase in resistance will result in a decrease in flow. A decrease in resistance will result in an increased flow. We can also look at the relationship from the flow's perspective. If there was an increase in flow rate, we can determine that there was a decrease in resistance. If there was a decrease in flow rate, we can determine that there was an increase in resistance. When applied to electrical power, resistance means to oppose or restrict something. This restriction impacts the amperage flow through the circuit. Just like in fluid power circuits, there is an inverse relationship between resistance and amperage. The electrical term used for resistance is called the ohm. It may also be referred to as impedance. A common abbreviation for resistance in ohms is either the letter R or the Greek alphabet letter omega. In this graphic, we see an electrical circuit with 9 volts DC power applied against a load called R1, rated at 100 ohms of resistance. Under this circumstance, we see the amperage of 0.09 amps existing in the circuit. Notice that this same amperage is found anywhere in this circuit, before or after the load, exiting or entering the battery. By increasing circuit resistance to 1000 ohms, Notice that the amperage drops to 0.009 amps, but the applied voltage pressure stays at the same value of 9 volts DC. Notice again that the amperage of 0.009 is the same value anywhere in the circuit. Increasing the circuit's resistance to 10,000 ohms results in a drop in amperage to 0.0009 amps. If we break the circuit, this increases the total resistance of the circuit to an ultimate value, resulting in the complete stoppage of the amperage. Going back to our original circuit, 9 volts DC is applied to 100 ohms of resistance, resulting in 0.09 amps. Reducing the resistance down to 10 ohms results in 0.9 amps in the circuit. Reducing the resistance further down to 5 ohms results in a 1.8 amp current in the circuit. In this graphic, we see virtually no resistance in the circuit. This is called a short circuit. Under this condition, the amperage theoretically increases to infinity. In other words, the amperage attains a very high value. There are really only two ways that electrical circuits can fail. They can either fail as an open line or as a short circuit. When a circuit develops an open line, it is as if there's a break in the component or a conductor. Under this break condition, amperage cannot pass through the circuit. When tested with an electrical test instrument, the meter will display an OL. This OL is meant to be understood as open line. This electrical diagram shows a break in the conductor between the load and the positive side of the battery. Because this adds an ultimate resistance to the circuit, it literally stops all amperage flow. The second way electrical systems fail is with a short circuit. Under this circumstance, there is very little resistance in the component. If we can predict amperage's value to the resistance it encounters, we can understand that under a short circuit condition, the amperage rises to a very high and dangerous level. Any electrical circuit can be damaged under a short circuit condition, and circuit protection must be used. An overcurrent protection device commonly used in electrical circuits are called fuses. Fuses have a rating in amps, and if the circuit it is protecting exceeds the fuse amperage rating, it will open, stopping amperage flow through the circuit. The electrical test instrument called a multimeter is commonly used in the electrical trades. The multimeter can measure voltage, resistance, amperage, and continuity. In this presentation, we will feature the steps to configure the multimeter to read resistance. The process to configure the multimeter to read resistance involves 5 steps. Number 1, set the leads. Number 2, set the selector switch. Number 3, set the range. Number 4, test the configuration of the meter for resistance. And then number 5, take the measurement. Step 1 is to set the leads of the meter to take the resistance measurement. For this measurement, the black lead is placed into the common or COM jack of the meter. The red lead is placed into the red jack marked R or omega. Step 2 involves setting the multimeter selector switch to read resistance. This switch is moved to the R or omega indicator position. Setting the range is the third step in the process of measuring resistance. What values displayed on the meter will indicate maximum values it is prepared to measure. Pressing the range button on the meter moves the decimal point to the right, increasing the measuring range. At this point, we want to test the configuration of the multimeter to read resistance. When the meter is configured to read resistance, the meter's internal battery is used and supplies the power for the measurement. If the leads are placed together as shown, the meter will display a very low value, perhaps 0.0 ohms of resistance, indicating it is configured properly. If the meter displays OL when the leads are placed together, the meter needs to be serviced by perhaps replacing the internal fuse of the meter. Before we take the resistance measurement, we have to remove all power from the circuit or device that we are going to measure. Taking a resistance measurement with a meter on a circuit containing its own power will result in meter damage, personal injury, or both. Again, before taking a resistance measurement, we must remove the power from that device. Not doing so will result in meter damage, personal injury, or both. In this graphic, we have removed the R1 load from the circuit before we measure its resistance. In this graphic, we are measuring the resistance value of an electronic resistor. Notice that the resistor has been removed from the circuit and has no electrical power being applied. The multimeter's internal battery provides the energy to take the resistance measurement.